Good morning, everyone. Good morning. Hope all is well. Hope everyone is doing all right. All right. Like everybody's in. Okay, we left off 5-3 last class. So we're looking at 5-4 today. And since that's the last section in chapter 5, that will probably be our only section for today. Good morning for those who are just getting in. Good morning. Yep. We're just looking at 5-4 today. Good morning. Good morning. All right. So conditional probability and the general multiplication rule. So last class we ended with which was it was probability multiplication rule for independent probabilities or independent events. So those were events that had nothing to do with each other. So in other words, if one event occurred, it had nothing to do with the effect of another event. So now when events are dependent, if one event occurs, it affects the other event occurring. So that's what we're talking about now, conditional probabilities. So the probability that F occurs given that E has already occurred. So the fact that E has happened affects the probability of F, occurring or happening. So you see that's a symbolism for it right there. My pin up. So this represents the probability of F given that E has happened or already occurred, and that line is what signifies that line between F and E. All right, let's scroll up, double title. All right. So that's the rule. This is how we will calculate it. The probability of E and F over the probability of E, or the number of E and F over the number of E. So it just depends on what information you have. If you have probability, you will use the first relationship, or if you just have the number, use the second relationship. But notice the positioning matters. So if you're trying to find the probability that F occurs given that E has already occurred, notice that E is going to be down here at the bottom. But if you were to flip it, that means F will be down at the bottom. So positioning does matter. Just making sure we didn't do this last class, right? We did stop at 5-3. Anybody can do a thumbs up or something, because I feel like I've done this before, but it might be because of last class. I mean, my last semester.
Yeah, this is new. We didn't do this class.
Appreciate it. Had a moment of deja vu, so glitch in the matrix. All right, so we're going to depend on this chart right here. Okay, thank you, sir. Thank you. We're going to depend on this chart right here, so I'll give you a chance to copy down the information. It's the marital status of males and females 15 years or older in the US. So the chart is in millions. So it's 41.6 million. So we have males, first column, females, second column, and then totals, third column. Never married, married, widowed, divorced, separated, and then totals for that bottom row. All right. Can we scroll up? All right, so he wants to use the table to answer the following questions. First, we want to compute the probability that a randomly selected individual has never married, given the individual is male. All right, so I need to go back up some. All right, let me know when you're ready to scroll up. All right, we're good to go. You guys a chance to write down both of those, and then we'll answer the question. So the second one, compute the probability that a randomly selected individual is male, given the individual never married. Was that for me or? Okay, guess not. All right, so let's look at A. Compute the probability that a randomly selected individual has never married, given the individual is male. So I'm going to call N never married M male, just for labeling purposes. Shorthand. So you see that we have, according to the wording, this would be our symbolism. We want to know the probability of N occurring given that M has already occurred. So I need to find the number for the chart of those that are never married and male, and then the total number of males. All right, so if you go back to the chart, never married and male is right here. And then the total number of males is right here. And so that's what we have, 41.6 over 122.5. All right. Questions on what we did there before we go to B? Yep, plug in the number from the chart. All right, we're okay to go to B. So B is very similar, just that it flips, basically showing the difference in the position. Remember, the position matters. If you want to know the probability of getting someone who's never married, given that the individual is female, probability is going to be different if you're looking for the probability of a male, given that the individual was never married. So here, this time, never married will be on bottom. The total number of people never married will be on bottom. Okay, so going back to the chart, never married and male stays the same, but now we need the total number of people that was never married, which is 78.5. And so that's where we got 41.6 over to 78.5. That'll give us 0.53. Questions? Any questions? Can I scroll up and we're still copying? Everybody good, right? Everybody good. Okay. So suppose that 12.7% of all births are preterm. Also 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. What is the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm? And then, is this unusual? Give you a chance to write it down. All right. So we have supposed that a 12.7% of all births are preterm. 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. I want to find a probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm. Is this unusual? So just like before, I'll go ahead and establish what I'm going to call these two events, these two categories, using W and P. So pulling from the problem, the probability of having someone, a baby that's preterm, 12.7%. And then the probability of having someone who's preterm and weighs 8 pounds, 13 ounces or more is 0.22%. So make sure you convert it to decimals properly. And then we want to know the probability that a baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm. So that's symbolism, and that symbolism sets us up for the calculation. And then here I was just emphasizing that W and P and W are the same thing. So that's our calculation, 0.0022 over 0.127 gives us 0.0173 or 1.73%. All right, everybody okay to scroll up? So remember the last statement was, is this unusual? The answer is yes, because the probability is less than 0.05, or in other words, 5%. Remember that was our marker for if something is unusual or not, if it's less than 5%. Any questions? Any questions? All right. So now we get into the general multiplication rule. Just multiplying the, if you want to know the probability of E and F, and really it's just a manipulation of this formula right here. If you want to know the probability of E and F, you can multiply the probability of E times the probability of F, given that E has already occurred. All right. So probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket given that he or she is pulled over is 0.9, what is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? All right. So once again, establishing a shorthand of which event, or what I'm calling each event. T is for gets a ticket, P is for pulled over. So probability of getting pulled over is 0.8. Probability of getting a ticket, given that you were pulled over, is 0.9. Got both of those from the problem. Now we want to know the probability of getting pulled over and getting a ticket. Use the formula. You multiply the probability of getting a ticket and the probability of getting a ticket the probability of getting pulled over, and then the probability of getting a ticket given that you were pulled over. That'd be 0.72. All right, any questions? All good. Everybody don't to read? All right. All right, so in a study to determine whether preferences for self are more or less prevalent than preferences for others, researchers asked individuals to identify the person who is most valuable and likely to you or your favorite other. Of 1,519 individuals surveyed, 42 had chosen themselves. So I'll give you a chance to write that before we scroll up to the actual questions. All right, scrolling up. So the first one, suppose we randomly select one out of 1,519 individuals. What is the probability that he or she had chosen self as the favorite other? All right, can we go to the problem? All right, so we want to know the probability of choosing one out of the 115, I said 115, 1,519 individuals that they chose self as a favorite other. So from the problem, we know we have 15, 19. That's how many people that were surveyed. Out of that group, 42 of them chose self. So this is just a regular probability problem, pretty much from the first section that we start discussing. You just take the 42 over the 15, 19, and that would be your answer. That's the probability of choosing someone who chose self as their favorite other person. Okay. Questions before we go to B? All right. So now here's where the new process comes into play, or pretty much what we're focusing on comes into play, is in B. It says if two individuals from this group are randomly selected, what is the probability that both chose self? Okay, get a chance to write it down, and then we'll get to it. All right. So we're looking at the probability that the first one we choose chose self, and the second one we choose chose self as well. So if we, I'm just writing all of that, writing everything out. So the probability the first one chose self, and then the probability that the second one chose self, given that the first one chose self. Now this one, how we set this up, we pretty much are using more so logic than a formula. So we know that the first one choosing self, the probability of that would be 42 out of 1519. Now the probability of the second one choosing self would have to be 41 out of 1518. Because if I chose one out of the group and that person chose self, how many people are left in the group that chose self? That would be 41 people. And then how many in the group are left, period? It would be 1518. So we would just count one down from both of our categories. All right. So in other words, once again, if I take one out of the group, how many people are left? Well, if there were 42 people who chose self and I took one away, then there's 41 left. And then out of the bottom number, the total number, if I took one away, it's 1518 left. So that would be the probability that's left, 41 out of 1518. So before we go to the calculation, is everybody okay with that? Make sure you're okay. All right. So calculation, multiply it out and calculate, get your decimal value, 0.0007468. All right. And math level, of course, will let you know how many decimal values to go out. Any questions on anything? Yep, it may. Yep, more than likely it will ask you to round it to however many decimal places. Yep, they'll let you know whether it's 2, 3, or 4. Yep. Just make sure you hold true to whatever they're asking of you. All right, so last one, dealing with this problem, compute the probability of randomly selecting 2 individuals from this group who select itself, assuming independence. So the key word here is independence. And we'll talk about re-emphasizing that in a second. Just give you a chance to write. All right, so now we're assuming independence. We're assuming that these probabilities are not changed, given that one has occurred. So it doesn't matter whether the first one chose self or the second one chose self, the probabilities will stay the same. So remember, we found initially that the probability of someone choosing self will be 42 out of 15, 19. And we would just keep those probabilities the same, multiplying together, and this would be our number. So if they're independent, then the probability just stays the same. Questions? Any questions? All right. So that was it for 5-4. Questions on anything I've said up to this point? Okay. So we're done with chapter 5. So like I said, this was the only section I was going to do today since it closes out the chapter. We will look to get into chapter 6 on Monday. You know, every day is, of course, opportunity for questions if you have them. And we'll just go from there. Did anybody have anything to say, comments, questions, concerns before we close out? Everybody good? Yep. All right. So I have someone that want to stay back and have a conversation. What about office hours, sir? Just did a question. All right, he might be typing. So if you guys are good, I'm good. Have a great weekend. Be safe, and I will see you on Monday. Take care. Yeah. All right, you do the same. Take care. Take care.
Mr. Tucker,
Yes.
you said to email you, and I
Yeah.
emailed you.
You didn't see my email this morning?
Mm-mm.
See, I sent my email. I covered myself. See, let me go ahead and put it, or let me make sure I hit send. Hold on. Hold on. I thought I sent it. Yeah. I said,
Oh,
yep. Do you see it?
yeah, I see it.
Okay, yeah. See, I was trying to prevent the fact that I hadn't got to it yet. They're trying to catch you before we got into class. But yeah, so I still got to map it out. It will. I'm thinking it'll be chapter 7, right? Either chapter 7, 8. Probably give you the lectures on both of those chapters. But I haven't forgotten y'all. I'll send it to you guys. Try to get it to you before the end of the day.
Okay.
All right.
Thank
Yep.
you.
No problem. You have a good one.
You too.
Bye. All right,
Hello?
sir. What you got, sir?
Hello.